the whole, how's everybody doing? And then I can record here as well, resume recording.
Recording in progress.
Okay, hello everybody, welcome to MTH 314 midterm tutorial. Thank you very much. My name is Adam. I will be hosting this tutorial today. So we're gonna help prepare, we're gonna work together here. We're going to get ready for this midterm. I took this course last year, but I took it with a different professor, so we didn't actually cover proofs at all. But I know how to do this stuff, so it's okay. I can manage. Because I read the textbook separately. How long will it take for me to post a video on YouTube? Hopefully quickly. Sometimes I forget, but hopefully quickly. Try my best. But Muse has this recording, so I'll that's gonna be there. But I mean, like, yeah, I'll post the video tonight. I can't promise you it'll be up the minutes this is done, but it'll be up tonight. I can't get the pen out of the thing here. There we go. No, it's good. So yeah, we're gonna be going for 2 hours today. We might take a little break in the middle, see how everybody's feeling, and yeah. Okay, before we begin, you can access my notes for this course. So again, I took this course with a different professor. We didn't do any proofs in it, but we did everything else and lots of other things. So my notes for this course and many other courses are available on my website, www.tutor.ca/notes. So I'll just put that in the chat, I guess, if people want to. I don't know if you can click links in the chat, but it is what it is. Maybe you can click notes in the chat. I mean, click links in the chat. Yeah, there you go. So feel free to take a look there. I also wrote separate notes for this textbook. So again, when I took this course, we didn't use this textbook. We didn't do proofs. But I wrote notes for this textbook, and I think those go up to 4 point something. But they're also they're mostly just like reference. They're mostly just like I took some things out of the textbook. So they're not as good as my regular notes. So I'd recommend looking at my regular notes for different things. All of logic is there, just not actually doing proofs. Okay, so that's that. If there's anything else I wanted to mention before we started, I don't think so. Hopefully everybody can see me and hear me properly. Like it sounds okay, and the video is not laggy or anything like that, or okay. All good? All good. Okay. So yeah, so my plan is let's start with the midterm. Let's start with the midterm, obviously, with the practice midterm that he posted, which I got, and then we can work from there. And if anybody thinks I'm going too fast, too slow, has any questions, feel free to let me know. You can unmute if you'd like to, or you can just message in the chat. I have the chat open. Totally up to you how you want to do it. Okay, so let's begin with this. It says let PQ and R be 3 statements, just general statements. Show that, and then a bunch of symbols, right? So let's understand what a bunch of symbols mean. So basically, we have a left-hand side, right, which is some statement, which is made up of P, Q, and R. And then we have a right-hand side, which is a bunch of statements. It's the same thing, made up of, a statement made up of a bunch of symbols. And we're saying that they're logically equivalent, which means that whenever this statement is true, this statement is also true. Remember, a statement is a sentence which can either be true or false. Which is either true or false, to be clear. So a statement is a sentence which is either true or false. So P, Q, and R are just placeholders for some kind of sentences, some statements. So we want to show that these are logically equivalent. Now you could do this by creating a gigantic truth table, but there's a little bit of a cleaner way of doing this, just using our laws of how these connectives work. So the connectives are like our implications, our nots, our ors, and our ands, and stuff like this. And because I always just, I'm bad at remembering, so or is that, and is that. Right. So I'm just gonna leave that on the screen because I often forget which one's which. So anyway, so we want to use our laws that we know to turn one into the other. Now, there's just so many symbols, it's better to get it more into a state that we're more comfortable with. At least that's how I think of it. So the first connective that we want to deal with is this implication here. And I like to just get rid of the implication. And the reason for that is it kind of just like makes things combine more. It makes more things combining. It's kind of like factoring. You want to just factor things so that you can cancel. I remember it looks like an A. That makes a lot of sense. I will never forget anymore how to do that. That's amazing. Is this you provided on the test? Okay, yeah, let's look at that. Perfect. I needed that. Thank you very much. Click to open. Amazing. So this is the sheet that will be provided on the test, which is amazing because we have all this stuff. Good. So we can go through this a little bit if there's anything that people want explained that's on here. Universal transitivity, universal modulus response, yeah, efficiency, yeah. Okay. Anyways, this is what we're going to be using for this question, so I'll just take a screenshot of that quickly. I'll put this here. So, okay. The first one we're going to do is, again, we're going to deal with the fact that we have an implication. So the implication is not here. Okay, not on here, right? I'm not blind. Is it on the other? Is it on the sheet here? Yeah. Like almost. That's basically it. It's just the not version of it. Why is there not just the normal implication? That's weird. Okay, it's fine. Maybe I'm just blind. Yeah. I'm just blind. I don't see it. Yeah, okay. So anyways, this is the basic thing. So the thing to remember, it's on there. It's kind of on there. It's just kind of weird. So anyways, P implies Q is logically equivalent to not P or Q. Yeah, not P or Q. So now that we have this this equivalence here, that we can turn this, like, this is true. This should be on this table. I don't know why it's not on this table, unless it is, and I'm blind, but it should be on this table. But anyways, so we're going to use that here to simplify these implications a little. I did this before because it's a little complicated, so I want to refer back to what I did. Okay. And what did I end up with? Yeah. Okay. So we have this statement that's true. What I'm going to do is I'm going to start with the more complicated side. Just like when you're like trying to prove a trig identity or something like that, you want to probably start with the more complicated side. So I'm going to start with this side here, and then see what happens. And then ideally, it kind of jumps out at you what the thing is to do, but it's good to just have a starting place. So the starting place is just with not. What kind of nots do they use here? Yeah, that. Okay. So not Q implies not P, or not P implies R. Okay. So first thing I'm going to replace these guys with what I was saying. So not Q implies not P, right? So using this, right, it's going to turn into, so Q, right? Yeah, how about I match this? How about this? Better just match it with colors. Let's just match it with colors here. That'll make more sense. Okay, so it's the inverse of the first thing or the second thing. That's what it is. The inverse of the first thing or the second thing. So the inverse of not Q is Q, or the second thing, not P. Right? Then from there, I want to OR this with not, and then the inverse of the first thing, which is P, or not R. Not R. Okay. Now, looking at this, right, it's still just a bunch of symbols, but what you should notice is that it's kind of like we have two terms. This is a term and this is a term, and both terms contain a not P. And that's the important thing to notice here, because then you can think of, oh, it's like a distributive property kind of thing. I can kind of like factor out that not P, and we absolutely can. It should just be R, yeah. It should just be. You're right. Thank you. So from here, that's the important thing to notice here, is that, again, like I said, we just have this not P and this not P. Now, just to make it a little bit more obvious, right, this is going to be not, did I distribute it before? No. Not, or did I? See what I did before. Face with that. Yeah, anyways, just to make it a little bit more obvious, this is going to be not P or Q, or not P or R. Okay. So what I'm going to do is I'm going to, oh yeah, this is what I do, right? Yeah, okay. Yeah, I can go over the first two steps again. So like the first two steps being from here to here. Is that like these two? Well, from here to here, I just switch the order of this. So you must mean yeah, you get from here to here. So basically, I just use this identity that we have for logical equivalent, like these are logically equivalent. So an implication is logically equivalent to this. And just the colors, just match the colors. The first thing inverted, and then or with the second thing. So that's all I did here. So you see how this, I turned it into the first thing inverted, is Q, ORed with the second thing. And then same thing here. The first thing inverted, ORed with the second thing. And that's all I do. So anyway, so continuing on. But if you need more explanation, feel free to let me know. Just to information on how to use the courses. We did not do this, Manna, when we were in this course. Actually, no, this we did. Never mind. What am I talking about? This we did. But the proof stuff later we did. Anyways, so I'm going to like basically factor out this negation here. It's basically De Morgan's law is what I'm going to use now. So you see, we kind of have a situation like this. That's what we have. And what's really important is that you like realize that these letters don't just have to stand for one statement. Like in this case, we have this situation. That whole thing is P from here, and that whole thing is Q from here. So you can basically use this law backwards now, right? And so you can take that negation out, and then it's just going to be the first statement, which was not P or Q, ANDed with the second statement, which was not P or R. So from here to here, just to maybe label what we're doing, right? From here to here, I'm using De Morgan. From here to here, I'm using, I'll make number 12. I don't know why it's not there, number 12. From here to here, I'm using number 1, right? Commutative. All I did is I just switched the order. Okay, then we're here now. So again, to recap, right? I started with this complicated one, and then I pushed it from the implications to something else. Couldn't we also use the rule not P implies Q? Yeah. Yeah, I guess so. Yeah, you could directly use that. You could directly, because you see you have a not of an implication. Yeah, you could use that. I think this made more sense to me doing it like this, but that would work. So anyway, so now we have this the statement here, and it's perfectly ready for you to use this distributive law, because you see you have like literally it's like you have like 2x plus 2y or something like this, right? The x is the q and the r is the y, and the 2 is the not p, and the plus is the and here. I know it's kind of a situation like that, but anyways, it's literally you can just like factor this out, right? And so you can literally just factor it out here too, but you need to just pay attention to the distributive law, how it actually works. So the situation we're looking at right now, it looks like this, right? Or does it look like that? Yeah, it does, right? It's no, it looks like this. Yeah, it looks like this. Okay. So it's something or something in a bracket and something or something. So we have something or something in a bracket and something or something, right? And these two somethings are the same. So that something can come out to the front and just or with the whole bracket, and you just and these two terms together, right? So see here. Oh, my video's kind of blocking. You don't need to see me. That happens way more than you think. There you go. So let me just repeat that because you couldn't see what I was drawing. So we have something or something and something or something. And the important thing is that these two somethings are the same. That's what I'm trying to say. These two somethings are the same. You can factor out that something like that. And I'm saying somethings instead of P and Q because I don't want you to get confused with the P's and the Q's and the R's here, right? So anyway, so the not in the front stays, and then it's not P that comes out, and that's being matching with that. It's being ORed, right? With and then it's gonna be Q and R, right? Because just matching this form, basically matching this form. So from here to here, I use rule 3. If anybody's confused, feel free to stop me. If everyone wants to explain anything better, feel free to stop me. I'll continue. So now, okay, we're here now, right? So what's this all about? What's going on here? I mean, at this point, we've done the thing that I mentioned at the start. I mentioned at the start that we kind of have two terms and you can like factor something out. So we did that now. So now what do we do? Well, at this point, you want to look back at what you're trying to prove. You're trying to show that this is equal to this. And super similar forms, right? P implies Q and R, and it's this. Well, I mean, we're just remember this rule, right? Basically backwards. This is by definition this rule, right? I'm using rule 12 again. Rule 12 again here, right? To turn it back into an implication. Why back into an implication? Because that's the form we have here, and we're done. We've shown that they're logically equivalent. I guess I should use triple equal signs this whole time because I'm saying they're logically equivalent, but notes will be posted. Yes, notes will be posted. They'll be in the description of the video. Why is there a double line? Okay. So that's that question. It's basically just applying a bunch of these rules in order. The difficulty is, I think most of the time the difficulty is coming up with the basically just seeing what to do, right? Seeing what to do next. Actually doing it is kind of tricky too, because you have to deal with these symbols, and the symbols here don't match the symbols here, but that's manageable. But the main difficulty is seeing what to do next. So I'm going to focus on that. You can also use a truth table for this question. It'd be a hell of a truth table, but you can use a truth table, absolutely. Do I know the name of law 12? It's just like the definition of implication, or not the definition, I guess, but it's the implication. I don't know. Yeah, I'm not actually sure that. But definitely necessary. I don't know why it's not on this table. I guess this table was in the textbook before you talked about implication. That's why. I can scroll down a bit. Yes. I'm confused why when we apply 12, you got rid of the not in the front of not Q. I got rid of the not in, like from here to here, right? That's probably what you're saying. So notice here, we have this quantity is like this quantity, right? And this quantity is like this quantity, right? So on the other end, on the other side, once you've done the transformation, it gets knotted, right? It's the inverse. It gets inverted. What's the inverse of not Q? The inverse of not Q is Q. And then, but this stays the same. This just goes from. Okay, someone said scroll down, so I'm going to scroll down there. Okay, so that's that question. There's detailed justification. Of course, you could use a truth table. I don't particularly want to spend the time doing that, but you could. And that's that. The next question is a truth table question. So let's do it. And then hopefully that explains why you would use it here. So the first thing to do is, okay, let's read the question. That's the first thing to do. I guess let me make it smaller so that my face isn't covering it. If my face is ever covering something, feel free to tell me. Obviously, I don't want my face covering things. So, okay, use the truth table to determine whether the following argument is valid. So we have an argument given to us here, and we want to determine if it's valid. Yeah, so basically what we're saying here is that this is the form of an argument. It's an argument form, right? Like it's not literally, there's no words here, but it was called a standardized form of an argument. And what that means is you're making some sort of claims. You're saying like, if this is true, and this is true, and this is true, then this must necessarily be true. And so when you make an argument in real life, if you're debating something, you might make an argument in this form, right? Kind of hard for me to come up with an example, but it's not too hard to go the other way, to go from the English to this, but it's kind of hard to go the other way. I don't know. Can't really think of an example off the top of my head. But when you're speaking in English, you certainly make arguments in this form all the time. Well, maybe not this exact form, but arguments which have a form all the time. Anytime you make an argument. So the main point is that we're saying in this here, if this is true, this whole thing is true, and this is true, and this is true, if the argument is valid, necessarily this is also true. As in, whenever these three are true, this is also true. If ever these three are true and this is false, then the argument's not valid. So that's what we need to check. Am I using the right words there? I know valid and consistent are slightly different. Let's just check that I'm saying the right thing. Argument is valid if no matter what particular statements are substituted in statements, if the premises are all true, the conclusion is also true. So yeah, so that's what I'm saying. So I'm not saying anything wrong. What's consistent? What's the difference between what's consistent again? Sound. An argument is sound if it's valid and all its premises. No, that's fine. Okay, I don't remember what consistent means again. But anyways, doesn't matter. So forget I was confused about that. Determine if it's valid. I think it's when it makes sense. Absolutely. Hopefully all of discrete math it's true when it makes sense. So we're gonna make a truth table out of this, and this is how we're gonna do it. I wrote on it, so now it's ugly. So let me find a clean copy. There. I'm gonna find a clean. I just want to. I wrote on it on my version of it, so I want a clean copy. Okay. So let's start. What you want to do is you want to make a column. You want your last 3 columns. Let me use the line tool. You want your last column to be not R, right? Your conclusion. So conclusion. Okay. And you want your last 3 columns, or whatever, your columns leading up to that, to be your premises, your major premises, right? So the major premises are just in reverse order. Not Q implies P. And then the next, I'm going to give up on the, no, I'm not going to give up on line. Actually, I will give up on the line tool, and you'll see a little magic trick that I do. I go like that, not a straight line, but then I can just do that. P or not Q. No, the order doesn't actually matter, but just to stay organized. Yeah, the order doesn't actually mathematically make any difference, but just to stay organized, because you want to identify a critical row, right? That's the whole point. You want to identify a critical row. So it's much easier if you just do it in order. P and Q implies not R. Not R. There you go. Okay, so in the end here, we're going to have a bunch of values, and then we want to compare it to the conclusion values, and that's how we're going to decide if this is a valid argument or not. But we have to build up to this, right? I mean, if you're like really good, you can just jump right to filling in these columns, but that's hard. I can't do it off the top of my head, so I'm going to just start putting things. So I see like a not Q and not R. There's no not P, so I'm just going to say a not Q and not R. So I'm going to put that in here first, right? Can I make the table closer? What do you mean by table closer? Can I make the table closer? Like bigger, or this is gonna be not Q, and the next one I'm gonna put not R. $10, I'm gonna run out of space. You make it closer to the screen. How do I make? I don't know how to make it. How do I make it closer to the bigger? Make the table closer to the screen. Yeah, it's bigger. Okay, bigger. Is it not? It's not big enough, or like it's blurry or something, or I can make it bigger. Totally fine. Okay, hopefully that's good. So that's as big as I can make it. So it sadly has to be good. So not Q. Oh, let me move this down again. Not Q and not R. So I'm just gonna fill that in now, right? So false, false, true, true, false, false, true, true. Not R is false, true, false, true, false, true, false. Okay. So how did I get these numbers? Just looking at what's given to me, right? So not Q is just you invert everything. Most people know this stuff from digital logic, so I'm not gonna add too much. But if you have questions, feel free to let me. So okay, we did that. Great. Now next thing is the connective. So let's do like a P and Q, right? That'll be something. Let me just kind of organize it so that I know I have enough room. P or not Q. That's it. That's all I need. Yeah, so I don't need this much space. Let me just say P or and Q. That's one. And then P or not Q. There's nothing else I need, right? Those are my 3 majors, and then the implication, and then da. Yeah, that's fine. Okay, so this is just gonna be an empty column here. Okay, so let me just make this a straight line. There we go. Yes, $10. I lost $10. My bad. Okay, so yeah, let's fill this in. Did I fill that right? No, it's supposed to be a not Q here. Oh no. What am I talking? Everything's fine. I'm second guessing myself. Anyways, so and connective, so P and Q. P and Q. True. P and Q. True. P and Q. False. 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 Great. P or not Q. P or not Q. True. 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 P or not Q. False. P or not Q. False. P or not Q. True. P or not Q. True. Again, just filling based on its previous interval. It's like small increments, and that lets you get to the major at the end. So now we're ready to do the. Oh, I guess I put the conclusion. The conclusion's already there. Whoops. So I guess I can just. I didn't even need that. I could just put that right here. True. 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 False. False. True. True. That didn't even need to be. I'm gonna erase all that. I thought I needed that as like a stepping stone, but that's actually one of our conclusions. So yeah. Okay, now we got to figure out these implications, but that's all there is to it. So okay, so not Q implies P. So this is true, remember, if this is true if not Q is false, or if not Q is true, and if not Q is true and P is true. Those are the two cases. That's literally what this means, right? So an implication is true if its hypothesis is false, so it defaults to true, which is why, right? If P is false, then not P is true, and it's OR gate, so it's true. And or if this is if P is true, which means not P is false, but Q is also true, so it still goes to 1. That's what that's saying. This is just it. That's just that in words. So we just have to do that. So first of all, I'm going to look through where is not Q false, because the implication will be true. Right? So not Q is false, false, and then these two rows are also false. Okay. And now we have to check where the hypothesis is false, so not Q is false, and the consequent, the P, is true. So it's kind of backwards here, so this is like our implication like that, right? So false, so that's fine, we already did that row. True, and also true, so that's true. Oops, my bad. I meant trues here. These were all supposed to be trues. Let me say that again, because I messed that up. If the hypothesis is false, the implication is true. Okay, so the false here gives us a true here. False here gives us a true here. The true here paired with the true here gives us a true here. Right? The true here paired with the true here gives us a true here. The false here gives us a true here. The false here gives us a true here. The true here paired with the false here gives us a false here. Okay? And then the true here paired with the false here gives us a false here. So sometimes negative, not Q is true, but P is false. That means they don't actually imply each other in that case. Right? In that case. So the implication would be false in such a case. Oops. If that didn't make sense, we're going to do it one more time with this, so hopefully it makes sense after that. And then if it still doesn't make sense, feel free to ask me questions. So again, this middle row, we're just ignoring. I just spaced it out too much. Well, not too much. This is fine. This is how I would do it. It's not a mistake. Okay, so now the implication here is this column implying this column. So it's like this, right? So wherever the hypothesis is false, the implication is going to be true. So it's true, 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 true. Now, just for these top ones, we just got to check, okay, if the hypothesis is true, is the consequent also true? So true, false actually gets us a false here. True, true gets us a true here. Right, so when I say this is the hypothesis, this is the consequent. This is the implication. hypothesis, consequent, implication. So there we go. Now we filled everything in. And I on purpose repeated not R, because you just want to put that at the end. Again, the order doesn't actually make any difference as long as your final step is right. But it just makes your life a lot easier if you just keep organized. So now we want to look at the, we have everything written. Now we just want to look at the critical rows. The critical rows are rows where all of your, what are they called? Predicates, your primary arguments, whatever. I forget what they're called now. I said the word a minute ago and now I forget the word. Where these guys are all true. The rows where these guys are all true. These are your, premises. They're called your primary premises. No, your major premises. Major premises. That's what it's called. They're your major premises. So, anyways, you want to look at where all these premises are true, okay? And you want to ask yourself, is the conclusion also true there? And then, so they are in these two cases, but not in this case. So we have a critical row where the conclusion is false. That means this whole argument is not valid. So we have a critical row where the conclusion is false, therefore not valid. Right? And so that's basically our definition of validity here. It's just that if all of these statements are true, then the conclusion must by necessity be also true. If that's the case, this is a valid argument, and you can make this argument. Okay, and this is valid in a method of proof if you wanted to use a method of proof using this argument here. Right? You know for certain that this would be true. If this was valid, it's not valid. So sometimes these three statements can be true, but the conclusion is not true. It's an invalid argument. All right, there's that question. So far, questions are taking us about 20 minutes each. Or is that true? No, that's not true. This question took 10 minutes. Whatever. So I guess about 15 minutes. So, yeah. I don't know. How's everybody feel about this question? Anybody want me to say something again? I have a hand up. Go ahead. You can talk if you like. Yeah.
Hi. For
Hello.
the second line, when we have the P and Q, and if statement 2 not R.
This guy? This
Yes. Yeah. Like on the table itself on the second line. When it goes from true to false, isn't that supposed to be a false over there and not a true?
Sorry, so second line, you mean second row or second?
Yes. Yeah. Sorry. Yes.
Second row here. Yeah. And so.
And then the answer for the P and Q, 2 not R.
Okay.
Isn't that gonna give us a false?
So you say this should be a false here?
Yes.
Okay, let's take a look at that. So that would mean, okay, so the P and Q is true, and that turns into no, it's gonna be true because Sorry, did you jump to that? Is that what it was?
No, I looked at R by mistake, but yes, sorry.
Well, R is what you want. R is what you want. R, right? P and Q implies not R. Oh yeah, you looked at R instead of not R.
Yeah,
Okay. No worries at all. Happy to have helped. That's good. Totally good. There you go. Okay. Imagine said if we don't label the far side with numbers, we get 0. So to the left of P, he said to number them. Okay. To the left of P? Oh, like the rows? Like 1, 2, 3, 4, 5, 6, 7, 8. And so identify that 2, 3, and 4 are critical rows. All right. I never heard this, but I'm not in the class, so makes sense why. Okay. Success so far. Hopefully. How's everybody feel? Okay? Am I making sense? Am I going too fast? I got a thumbs up. A good sign. 1 thumbs up out of 90 people. Pretty good success rate. All right, good. There you go. Okay, more thumbs up. Yay. Okay, good. I just want to know, like, if anything I can do to change. I'm happy to do that. Okay, let's move on. So next one is what is the next one? Too many tabs. Next one is this question. So it's a little bit of basic proofs that we have to do. So prove following statement is true. Okay. So, all right, got a bunch of brain power for the midterm. That'd be good. This is my attempt to lend some brain power here. My attempt. Okay, so question 3: prove that the following statement is true. So we got a big statement here. I'm gonna first translate it to English, and then we're gonna just prove it from symbols. So this is saying that there is some real number y. Okay, there is some real number y. Some real number we're gonna call y. Which, okay, has the property that, okay, which, dot, didn't mean to do that, which, dot, has the property that for every integer x, x squared is bigger than y. Okay, so there's some real number y, which when you take any integer and square it, all those squares are going to be bigger than the number we chose. And so you can prove this by just producing an example of that number y. There doesn't have to be a unique number y. It's just saying there exists one, at least one. So I guess there is at least one real number y. 0, sure, right? 0. In my example, I put -1, right? Exactly. So when you square an integer, you'll always get a positive number. So yeah, y equals, I put negative, my answer is -1. But anyways, y equals -1, or really any y which is in the set 0, well, it's a real number, right? So any which is in inclusive of 0 to negative, well, I guess negative infinity to 0, right? Any y that's in there would be a valid answer to this question. So I just chose y equals -1. So just to verify this, well, it's strictly larger than. Wait, 0 doesn't work because then 0 is not larger than 0. Oh yeah, 0 is not larger than 0. So if x was 0, 0 squared is larger than 0. That's false. Yeah, you're right. Yeah, you're right. So not inclusive of 0. Yeah, 0 is not an option because 0 squared is 0, and that would be false. This statement. Yeah, that's correct. So y equals -1. That's what I said in my answer there. To avoid any of that, that was my written answer. So there you go. Just to verify here quickly, right? So if I just choose any x, let's just say, so verify. Not proving anything by doing this, but just verify. Like choose x equals -3, x squared is 9, and 9 is certainly greater than -4. So we've verified our statement, which is true. And so yeah, so we've proven it by just producing an example. So that is a totally valid method of proof to prove something like this, which is just claiming that something exists. So if you can just show that the thing exists, then there you go. Okay, that was a quick one. So I'll move on, but feel free to stop me. Feel free to raise your hand if you want, but you can also just unmute if you want. As long as we're not many people talking. Okay, so next question, I lost now, is this guy. Not too bad. Someone asked a question. I don't think it makes sense because the y has to be less than all domain of z. Not the domain of z. Careful. So you're right. If this was x, you'd be right. Then the y has to be less than every integer. There is no such number. There is no smallest integer. But this is x squared. Remember, x squared, the range of x squared is 0, 1, 2, 3. No negatives, right? So we just have to say that there is some number that's less than all the positive integers, all the natural numbers, including 0. So that does exist. Right? So I think you're thinking there's no squared here, right? No problem. So what did I do? Did I take a screenshot? prove the statement is false. One way to do that, always, to prove a statement is false, is to show that the inversion, in the negation, or whatever you want to call it, is true. If you can prove that the negation is true, then you've proven that the original statement is false. Because P, basically because P and not P is tautology, or whatever it's called. Tautology? Tauology? I forget what it is. It's been a little while since I've said these words, but yeah. So anyways, basically that's why. Tautology. There you go. Tautology. I got it right the first time. So because of that, a statement and its inverse cannot both be true. So that's why we can use this as a method of proof to prove that something is false. Okay, so let's get into it. So what's the statement? Y is there exists a real number. Again, I'll just translate to English. I just find that kind of fun, so hopefully it's helpful as well. Make the text a little bigger. There is at least one. There is at least one number y. Or I guess I'll do it over here. That which has the property that the inequality x squared minus x is what I say x squared. X is less than y cubed plus 7 is true for all x. Okay, so let's just first of all, let's just sort of play around with this a little bit and just see if we think that there is a number, because it's telling us it's false. But let's just try it. So obviously, but let's try it. So which there is some number such that this is always true regardless of y, right? Well, this is saying that I do something to a number, whatever, y cubed, if y is some number, then y cubed is some number, add 7 to it, so that's some number, right? That basically that x is always, basically, this is bigger than any number x. That's what it's saying, right? It's saying that whatever I get over here is always bigger than any number I could ever choose x. Basically, this statement is saying there is a largest real number. That's what it's saying. It's saying this is saying there exists a largest real number. Because again, if y is just some number, then y cubed is some number, and y cubed plus 7 is also some number. So that would be the largest number. And we're saying that y cubed plus 7 is that largest number. That for all x values, this is going to be bigger. But that's certainly false. There is no largest real number. Infinity is not a real number. So yeah. Okay, so we need to prove that this is false. So again, the way you do this is you negate it, and then you prove that the negation is true. So just for completeness, I'm just going to rewrite it. So negation of there exists y is an element of all real numbers, such that for all x, which are real numbers, then the predicate, which is x is less than y cubed plus 7. Negation is true for any x plus k. Yeah, where any k enters is greater than or equal to 3. That's correct. Yeah. So you could use that to prove. You don't even have to actually even do negation, but yeah, that's right. So let's go through it. So you want to take the negation of this statement. Now, how do you take the negation of this statement? Basically, you just treat this as like a little unit, right? That little unit. And then what you want to do is you want to, okay, so first of all, existence flips to for all, right? There exists switches to for all, and then you negate the predicate, right? You negate the predicate here. So it's going to be for all y, which are real numbers, for all y real numbers, this is false. This is false. So not there for all x x is less than y cubed plus 7. Right? We're making our way. Next, we got to negate this. So for all y there exists some x such that, and then you just negate not, x is less than y cubed plus 7. I'm just doing it really step by step here, just so you understand, right? So you just keep pushing that negation further and further down. And then, so for all y in R, there exists some x in R such that, and the negation of this is that x is greater than or equal to y cubed plus 7. This is clearly true, right? This is clearly true because we can do this by just picking some x, right? So we're saying, okay, why is this clearly? I said this is clearly true, and some people shook their heads. So we're saying that for any number you can choose, there is some number bigger than that number cubed plus 7. So for any number you can choose y, if you cube it and add it to 7, there's some number bigger than that. That's true, right? There's no biggest real number, right? So yeah, okay, so this is true. We can just choose, I'll just say pick y, whatever, y to the 4 plus 7, or y cubed plus 7 plus 1. Right, pick x equals that. Pick x equals that, right? Just one bigger. There you go. When we negate the less than equal to because greater than, or when we negate the less than, it becomes greater or equal to. Yeah. So the negation of this is that. And then the other way is also, of course. So yeah, so now you just have to pick some x value that satisfies this. Yeah, this certainly satisfies this, right? This is just the next number, so it is certainly bigger. And technically, you also have to prove that x is an element of all real numbers, but maybe you don't have to prove that. I don't know. I'm not totally sure. It's not too hard. Well, you do. Yeah, okay. I guess you don't need the plus 1. You're right. You could just choose x, but I want a little bit like make it a little bit easier to understand. You're right. Technically, you don't need the plus 1. Can't the first statement also be true if x equals y? The first statement, this statement, or whatever, this original statement? If x equals y, no. Yeah, if x equals y, then no, it can't be. Why couldn't we pick at the original statement? Yeah, it's hard to show this order, right? That there doesn't exist something. Basically, you'd have to go through. So sorry, the question was, why couldn't we pick at the original statement? The reason we couldn't pick at the original statement is because we have to show that there is no such number, which means we would have to go through all the real numbers and show that every single one does not satisfy this. But that's very hard to do. Probably some loopholes, probably some way to go around having to do that. But just off the top of my head, you'd have to show that every real number does not satisfy this, and that is obviously not possible to do. So it's better to just negate it, and then it's easier to disprove a universal statement. So yeah, so assuming x is a real number, which it is, because if you cube a real number, it's still a real number. If you add if you add 7 to a real number, it's still a real number. If you add 1 to a real number, it's still a real number. So now x is a real number, and x is a real number that satisfies this. So we have therefore proven. So I don't know. Therefore proven. I don't know how to end it, but there you go. When you have an exists, then for all, that means that there is an object for all other objects. Therefore, for the original statement, y cannot be dependent on x and y, and y equals c a constant. Yeah, you could make x dependent on y cannot be dependent on x, but x can be dependent on y because that's what we did here. We picked it. But yeah, that's correct. Makes sense to me. Y is some real number, any real. Yeah. Right, any real. Okay, so there we go. That's that done. So the negation is true. What did I write in my notes when I did this? Not much. Oh, did I have the order wrong? Oh no. It's always true. Oh, I just did the order wrong or something? What did I do? Oh, when I did it in my notes, I did the order different. Anyways, doesn't matter. Same thing. This is correct. What we did here is correct. Okay. If there's no arguments, I will move on. And we don't have that much questions left, right? Because question 7's not there. Yeah, we only have 2 more, and they're very short questions. So maybe let's do those 2 short questions, take a 5-minute break, and then we're going to move on to other stuff after. How would we modify Q4 to make it true? That's a good question. I mean, you could you could make it equal, couldn't you? Let's see. If you made it equal, then you could just choose. Yeah, right. You could just make it equal because there exists some y such that. Oh no, that wouldn't make sense. Is that for all x, this is greater than or equal to x? Yeah, no, or equal. Oh no, not for all x. Never mind. That wouldn't make sense. Okay, I mean the other way. Or would the other way make sense either? Yeah, you can restrict the domain for sure. You could do it the other way so that x, for all x is greater than this value, which is saying that this is the smallest, basically, you're saying this is the smallest real number. There's still no smallest real number. Yeah, you could restrict the domain. So yeah, it doesn't matter. Flipping the sign doesn't matter. I think the flipping the sign wouldn't matter because then you have this, you're just saying this is the smallest number. But that's clearly not true because you could just not add 7 to it. That would be smaller. So that's not true. But yeah, you could just you could restrict the domain to be just something else like that. Restrict the value so that x has to be less than. I think for less than equal to. So if I put you're saying if I put this equal to here, we restrict the values of x, so x has to be less than. Well, yeah. Then that would be true. Yeah, but that's not that's kind of trivial, right? But yeah, that's true. Okay, let's move on to this. So, disprove, approve, or disprove. Clearly state your answer, true or false. So that number is divisible by 12. Or you could rearrange the quantifier. This number is divisible by 12. So this is really not that hard. You just have to basically show that this is 12 times, whatever, some q, whatever. If 12 times if that number is x, if you can show that x is 12 times some q, where q is an integer, this implies that x is divisible by, or 12 divides x, which is not that hard, right? So you just factor out a 3, factor out a 2, factor out a 2. So it's going to be 3 times 2 times 2. It's going to be k minus 9, k plus 3, k minus 3, k plus 3, and then k minus 15. And that's 12 times whatever, right? All that stuff. I'll just write it again. K minus 3, k plus 3, k minus 15. And so we've successfully written this as 12 times q, therefore 12 divided. Not too complicated. This is, and this is an integer. Sorry, I should have mentioned that this is an integer. So if this is an integer, we know this is an integer because k minus 3, k is an integer, right? It says for every integer k, right? So k is an integer. K minus 3 is also an integer. K plus 3 is also an integer. K minus 15 is also an integer. Now, if you multiply integers, you still get integers. It is closed under addition and multiplication. Yeah, exactly. That's what I'm saying. So there we go. You could multiply it out, but probably wouldn't help too much multiplying it. I don't know how picky. I have no idea how picky. So like, yeah, if you are, I don't know how picky. Maybe just say like that this is an integer. This is q, which is an integer, and that might be enough. If I was the marker, I'd probably say that's enough. But yeah, there's varying degrees of detail that you're allowed to put into these proofs in reality. I don't know in this course, I'm not sure, but in general life, there's varying degrees of detail that some things are just implied, like it's obvious that this is an integer. But to be totally technically correct, you would take that. Okie dokie. Let's do next 2 questions. They're really not too bad, and then we'll take a short break. For every integer. Yeah, I didn't assume k was any particular integer, right? I didn't say, I just left k as an integer, and whatever integer it is, q is also an integer, this integer here. And it's 12 times q, so it means it's divisible. For all integers a and b, if a is odd, then a plus b is odd. I love these kinds of questions. I don't know why. I like just showing things are odd or even. I don't know. It does become a little repetitive, but I'm a fan of it. So a, b are integers. A is odd implies that a equals 2k plus 1. Say minus 1. I don't know what you guys say. I say plus 1. Why is 2 in an absolute sign? That's a very good question. Totally understand why you say that. It's 12 divides x. That's what I'm saying. 12 divides x. Totally understandable to think that looks like absolute value of 2. My professor for signals wrote 1 over t, and I stared at this for so long, and I was like, why is he drawing a capacitor? Why is he drawing a capacitor? It made no sense. Like, why? This makes sense to draw a capacitor at the beginning of the question. And I was like, stared at it for so long. And then it finally clicked that it's 1 over t. But that's just a side note. So, for all integers a and b, if a is odd, right? No, it's crazy. For all integers a and b, if a is odd, then a plus b is odd. So, if a is odd, that means a is 2k plus 1. I'm going to say 2k1 because I use k's. You can use whatever letters you want. I just say k1. So, it's 2 times an integer plus 1. Great. Then a plus b is odd. Well, it depends on if b itself is odd or not, right? So b is either odd or not odd. Yeah, you could disprove this by counterexample. Sure. Yeah, actually, that would totally work. So let's just quickly do that. I'll show you how to do it mathematically, not like by direct proof. Shouldn't say mathematically. It's all mathematically, but by direct proof after. But yeah, counterexample. So I'll just say counter. So if a is odd, 3, then a plus b is odd. Well, not if I add 3 again, right? So equals 6. Odd, not odd. Well, even, which is not odd. So therefore untrue. Untrue. Great. I'll just show you how to do it properly here. I'm not too complicated. So it depends. You can break it into 2 cases, right? There's 2 exhaustive sets for this kind of stuff. B is either even, B is even, B is odd. If B is even, this is actually true. So if B is even, this is that means that, so we have A is 2k1 plus 1, and B equals 2k2, 2k2. And then A plus B would just be 2k1 plus 2, plus 1, I mean, plus 2k2. And now you can just factor that into 2k1 plus k2 plus 1, which is, therefore, A plus B is odd. This is assuming that B is even. But if you don't assume B is even, which is the other case, right? So you got to check both cases. This is where we have A is 2k1 plus 1, and B is 2k2 plus 2, plus 1. And A plus B is 2k1 plus 1 plus 2k2 plus 1, which is 2k1 plus, well, 2k1 plus 2k2 plus 2, right? Which is 2k1 plus k2 plus 1, which is even. Therefore, A plus B is even. This is what I showed here, right? If I do 2 odd numbers, they're going to add to even. And that's whole because I could factor out the 2 from that 2. This is some integer, right? This is some integer. This is also some integer. So disproven by long way, disproven by counterexample. Whatever. Okay. Could you just write the original statement in logical form? Sure. I like that question. We're saying that for all a, b, which are integers, a equals, well, you can be really technical here, but I'll just say a is odd, implies a plus b is odd. If you want to be really technical, you could say a equals 2k plus 1 implies a plus b equals 2k2 plus 1. But that's, I wouldn't write. I don't think anybody would write it like that. It's better just write it. Since I believe if you rephrase it with only if, and it will be true. For all integers, a and b, if and only if, so if a plus b is odd, if and only if a is odd. Only if, yeah, which is the same thing as if and only if. A plus b is odd only if a is odd. If a, so you're saying that if a is not odd, if a is not odd, then the answer will not be odd. As in, if one of the values is even. Yeah, that's correct what you're saying. If one of the values is even. No, is that correct what you're saying? A plus b is odd only if a is odd. So if a is not odd, a plus b is not odd. Which means if there's an even number, a plus b is... No, that's not true. Because if there's a plus b is... Yeah, that's not true. A lot of questions. Amber K1. Okay, I don't think you can use if only if because everything. Yeah. So there's this question about the K1, K2, right? K1, K2 are just arbitrary integers, right? That's the whole point of saying that b is even. It's 2 times some integer. It's an integer and it's 2 times some integer. That is by definition even, right? Because it's divisible by 2. Okie dokie. Last question we'll do from this test. I got some others to do after. Proved by contraposition. If xy is even, then x is even or y is even. So this is just nice to write as an implication. So xy even implies x even or y even. Oh yeah, the conclusion for the last one is false. Yeah, proved it by counterexample and by just direct proof. It's false. Or that I guess that sometimes we've proven that that this is not always true. That's what we prove. This statement can sometimes be false, so it's not always true. Basically, this is like showing a way to find a counterexample. That's kind of a better way to do it. This is like an algorithm that tells you how to find a counterexample. The counterexample is the actual proof. Contraposition means contrapositive. X and Y are, yeah, it doesn't actually say. It should say, I guess integers, yeah. So xy even implies x even or y even. So contraposition is just flipping it around, right? So you say not just flipping around. So x, you negate both of them. So x, not x even or y even, implies not xy even. Let me put the word is. It's a little weird if I don't put the word is. Is. So not x is even or y is even implies that xy is not even, right? Xy is not even. So this is easier to prove, right? Because if I distribute this in a little bit, basically this is x is odd and y is odd. Right? Hopefully it makes sense why it's switching to odd, right? I'm negating it. Implies xy is odd. This is much easier to prove. So you can just do this by doing the whole x is equal to 2k 1 plus 1. Y is equal to 2k2 plus 1. So xy is 2k1 plus 1, 2k2 plus 1. Question, do you have to flip the xy and x or y as well from the original statement. Yeah, like negate it. Yeah. You negate it. Yeah. You negate both sides. Okay, and so now we just gotta basically we've looked at our hypothesis. Our hypothesis is that the two numbers are odd, and we're looking at the conclusion, which is we now just have to show that this is odd. Yeah, so I guess I should have been clear. What's the contrapositive? If you have P implies Q, the contrapositive is not Q implies not P. And the important thing is that these are logically equivalent. These are logically equivalent. So if you want to prove this, you can just prove this. Anyway, so foiling this is going to be 2k1 or 4k1 k2 plus 2k1 plus 2k2 plus 1. Factoring out the 2 here, so you get 2k1 k2 plus k1 plus k2 plus 1. This is some integer. Therefore, xy is odd. Sometimes I go a little crazy with the y there. You're missing a 2. Missing a 2. Make sense? This question? Okay. Hopefully. So, okay, let's take a 5-minute break. And then everybody get some water. I'll have a little snack of banana. And then we'll start again in just 5 minutes. And then we'll do, I got some questions sent to me. So we'll do those questions sent to me. We'll go until 8. Sound good, everybody? Scroll down, please. This is the bottom. There you go. Int. Well, the fact that it's an integer doesn't imply it's odd, but the fact that this is written as 2 times some integer plus 1, that's the definition of odd. That's the definition of odd. Okay, guys. 5 minutes. I'll go back to, well, what should I go back on? The questions I'm going to do are sent by the students. Sent by a student. Break. Back at 7:10? Not 7:10. Break. Back at, can I change the text? Hello? Seven 23. Okay, guys. 5 minutes. Back soon. Okay, guys. I'm back. Let's keep going. Hopefully everybody had a nice few minutes. Let's continue on with some of the questions I had planned here. Basically, after this, it's just like your guys' suggestions. So I have one here, and I got 2 emails. So we'll look at those questions like this. That over. I got this one question from before. Hopefully it's not too blurry. Yeah, it's doable. Okay. So consider the following statement, that statement. Which of the following are equivalent ways of expressing the statement? So I think the way that's probably good to solve this, that's going to be bugging me. I wrote on purple on it. I can't erase it now. Okay. Probably a good way to solve this is just write all these in symbolically and see if it's the same, right? That's a little time consuming, but maybe it's also good practice, right? Not going to take too long. So all integers have even squares and are even, which means for all x, e, z, right? For all integers, x squared is even, and I guess I should say, x is even. This is not this, and also clearly not true. Not every integer is even. Any given integer whose square is even, that integer is itself even. This is saying for all x, which are integers, for any given integer whose square is even, x squared is even implies, given any integer whose square is even, that integer is itself even. Implies x is even. I have to read it a few times to actually do it, but there you go. Exactly this. So B is definitely one of our answers. It's also very provable. We can just prove this quickly. Yeah, right? Yeah, I think it's very provable. For all integers, there are some whose square is even. So this is basically saying there exists an integer x, I should say n, but whatever. We're this far into it, such that x is even. True, but not what this is saying. If anybody has any questions about what I'm writing here, feel free to let me know. Any integer with an even square is even. Yeah. So, it's gonna be copy this again. That's what I'm gonna say, right? It's gonna be any integer with an even square is even. So it's saying for all integers, x squared is even means that x is even. I'm just gonna copy that again. So that's also a solution, right? If the square of an integer is even, then that integer is even. Again, it's if you just try to turn it into symbolic form, you're always going to write this. It's an implication, and you're making a statement about all integers, x being any integer. And this is always the implication you're making in that statement. You can phrase it however way you want, but this is also totally a solution. So that's the same, that's the same, that's the same. All even integers have even squares. This is saying for all x, which are integers, I think is making it weird. For all x, which are integers, not real numbers, all even integers have even squares. If x is even, this implies x squared is even. Right? That's what this is saying, which is not exactly true. Converse error. Which is not well, sorry, truth or not, which is not the same as this. Right? This is saying the other way around. X squared is even implies x. The square of an odd integer is odd. So this is saying for all x, I think it's making a weird noise. I don't know why. Anyways, for all x which are even integers, or which are integers, if x is odd, this implies the square of an odd integer that x squared is odd. This is equivalent to our original one. And that's because I can do the contrapositive of our statement here, right? Which is saying for all x, which are even number, which are integers, I mean, if x squared is even, I can get rid of the word if. I don't need the word if there. X is odd implies x squared is odd. So x squared, not x squared is odd, implies not x is odd. Right? That's the contrapositive. I'm just doing the contrapositive. I'm switching the order and I'm just nodding it, but nodding this is just saying it just means it's even. Even. So there we go. That's the same as the original statement. Right? So it's just contrapositive. And the contrapositive is equivalent to its original statement. An implication is equivalent to its contrapositive. Okay. Question 5. Didn't read this yet. I don't know what it is. Rewrite the following statements without using quantifiers or variables. Indicate which are true and which are false. Oh yeah, I wanted to prove this. I don't know. Do you guys want to see me prove this? Can I get a vote? Thumbs up, thumbs down? Did I prove this? 1 thumbs up. So far, thumbs up's winning. If there's even one person who doesn't want me to see it, me to do it. Gotta vote with thumbs up, thumbs down. Okay. There's 2 thumbs ups. Let's just do it quickly. It's good practice. Whatever. So we're saying that n squared is even implies n is even. So yeah, I guess I'll prove this by contrapositive. So n is odd implies n squared is odd. So if n is odd, this is n equals 2k plus 1. N squared is 2k plus 1 squared, which is 4k plus 2 plus 4k. No, sorry, plus 4k plus 1. And I can factor out a 2. So it's going to be a 2k k squared plus 2k plus 1, which is odd. So I've proven this, which is equivalent to the original one. Done. Good. So there you go. Let's look at this. Okay, so rewrite the following statements without using quantifiers or variables. Indicate which are true and which are false. It's using quantifiers and rewrite in English. Let the domain of X be the set D of objects discussed in mathematics courses. Okay. There's no D here. Let real X be X is a real number, and positive X be X is a positive real number. Negative X be X is a negative real number, and integer X is an integer. Okay, so I mean, I guess we can. It's kind of here, right? But I'll just show what my thought process is when solving this, right? For all X, if X is real, so I immediately say the word if here because of the implication, right? So for all real numbers X, for all X, if X is real and X is negative, this implies that negative X is positive. So for every number, if X is real, and is real and negative, then negative X is positive. But there's no symbols here. Every real negative number has a positive. Yeah, okay, I guess so. Sure. So you can even remove more variables there. Yeah, I guess that's you can remove more variables there. So this is one step down. This is English now, right? But this is saying like for every number, if that for every at this point, yeah. So you can just sort of start combining things. So instead of saying for every number, if that number is real and negative, just skip right to every real and negative number. Every real and negative number. That whole thing is just every real and negative number has a positive opposite. So we usually don't use the word, like we don't often use the word opposite in math to say negative, but anyways, that is the actual word. So the opposite of X is negative X. Whatever. And now I'm just copying it. So has a positive opposite. But just to kind of do it like this. So this is probably how I would approach it, right? I would translate into like somewhat English first. Well, English first. And then way more English after. If you want to completely remove variables. When I answer this, I say for every object discussed in mathematics courses, if it is a real and negative number, then its negative will be positive. Yeah, it doesn't actually say that X is. Oh, sorry, no. Let the domain of X be the set D. Okay, yeah, I saw that. For a second, I didn't say it here. So, it says the domain of X is the set of all its objects. So you correctly identified that to be that. So, yeah, that's fine too. Okay, and then for part B, do you recommend that in the midterm we write the formal translation to English, then change this normal English? Yeah, I would probably do it. I would do this exactly like what I said here. I would translate to that and then translate to that. Exactly how I would do it. For B, they're saying there is some real number that has the property that it's real and it's not an integer. There is some real number. There is some, not some real number, some number. Or technically some object discussed in math classes is the more precise thing. But anyways, we're not trying to be precise, we're trying to translate to English. So there is some number which is real and not an integer. That one's easy. There exists a real number which is not an integer. This is also a true statement. You have to prove it. You can prove it by producing an example. But yeah, I guess that's D, not B. That was B. That was D. But yeah, there you go. that's that. That one's easier, I think. No implication. Maybe the implication is the difficult part of the first one. Okay. So I will move on now to the email questions, but feel free to ask any questions you have in the chat. Okay, so first question I got was to prove a bunch of these guys. So how much time do we have? We have about 25 minutes left. Yeah. So yeah, we should probably go through all these. So just prove all these things are true. So go for it. Oh, could I explain the B one more time? The B one? Yeah. So just first from here to here, and then from here to here. So from here to here, it's saying that for every number x, if this, then this, right? That's the form we have. If this, then this. What does this mean? This means real and negative. So if it's real and negative, then the opposite of it, negative x is going to be positive, which is true, right? If you have a real negative number, negative x is going to be positive. Negative 2 is 2. So, oh, and then to here is just like you just want to kind of start combining things. So instead of having a variable, just instead of saying for every number, if that number is real, too much repetition. In English, we don't say that kind of stuff. For every real and negative number has a positive opposite. That's all. Okay, so first question here is, for all x, which are real numbers, there exists some y, which is an integer, such that x is greater than twice that y. This is true. Probably, do we get a cheat sheet? Yeah, so there's this is going to be posted, which we can go through. So this is going to be, according to someone in the chat here, I forget who, but someone in the chat here sent this. And this is going to be on the test. Scrolling too fast, sorry. Go to the top. Anyways, so probably how I immediately look at this and I say, okay, it's a little bit of a confusing wording here. What if we just say x over 2 is greater than y? Same thing, obviously, right? Same thing. There you go. Thank you, Krish. So there's the cheat sheet. So x over 2 is greater than y. That's equivalent, right? And so now it's a little bit more clear because we're saying for all x values, there is some y value which is less than half x. And this is true, right? We can pick y is x over 2 plus minus 1. Right? If we pick that, that's clearly true, right? So all we're saying is that if for every x value, there exists some integer. Oh, that's not an integer. Not necessarily an integer. So I don't know. Multiply by 2. There you go. But that isn't true. X is, for all x, there is a y. Like you're saying, because it's not an integer. Okay, yeah. Yeah, okay, I guess you're right. So you could say floor minus 1. That's what you could say. Yeah. Or ceiling. I forget which one's floor or ceiling. But anyways, you can say that. Right? Just round down and then minus 1. Probably don't even have the minus 1. But anyways, just round down. And minus. Just minus 1 as well, just to be safe. Yeah, so you just have to show, basically, to prove this, you just have to show how you get that y value. If you can show a way to get that y value, and importantly, that works for any x, then you've proven that the statement is true. And I can successfully get this y value. And that makes this true, right? If I try it, well, it's a little hard to, because it's not going to rearrange. But this is true, right? Because equivalent to this, x over 2, y is smaller than that x over 2. So if I just take that x over 2, round it down, subtract 1, that's certainly smaller than x over 2. If I take a number, round it down, subtract 1, it's certainly getting smaller. It might be easier to disprove the negation. But I'll leave it at this for now. So this is true. This is how you generate a y value. If you can show how to generate the y values, that's fine. Which satisfy. So yeah, there you go. That's that. Okay. Yeah. I mean, it's fine. You could just what could you do? Yeah, if you're not allowed to do that, then you could just take the square root. No, you can take the square root. You could well x. Yeah, but it's not an integer. Yeah, you have to floor it. Yeah, question?
Hey, I
Hello.
have a question about the existential quantifier, actually.
Go for it.
When we're assigning a value to, let's say x, we're allowed to assign it a value of y as well?
So you can't, yeah, so you're saying for x here, yeah, you can't choose what x is. X is any real number, and the point is that you can't control what x is. But you can control y, because the claim here is that for any x value, x can be literally anything, I can figure out some y value, which is an integer, that satisfies this. That's what it's saying. I can figure out some y value, and that's fine. You can base that off of x. But x is just any x value, any real number, and you can't control that. Does that make sense? Does that answer the question?
Yeah, it does. I just there was an example. I just sent it to you. It kind of confused me earlier.
Yeah, you sent it to me how? Via
email.
Email? Yeah. Sure. Let's take a look. Oh, maybe. Okay. So consider the statement: there exists some real number such that for all y values, x plus y equals 0. There exists some x value. Oh, that's not true. Is that true? That's not true. Yeah, the statement is false. Okay, that's not true. So rewrite the statement in English, expressing. So there is a real number. Yeah. So what particular part? Is it this particular part that you want, like, that you have trouble with? Is there any particular part, Joshua, that you want me to?
I was confused. Let's say for C, why we couldn't make x equal to negative y, in which y minus y would equal 0.
Yeah. So you can't control. Well, yeah. This is saying that there exists some x, some specific x, that for every other number, real number, if you add that real number to it, you get 0. And sure, that's true in like one case, right? Like, let's say I'm going to choose x is 2 or negative 2. This is only true if y is 2, right? But you can't just, you can't change x here. You can't change x here. This is just saying that, like, here, there is a real number, not a real number based off the other number. There is some real number whose sum with any other real number is 0. And that's just not true. There is no such number.
Got it. Thanks.
Right? And I think the main point of confusion is that it's one number. We're saying there is one specific number, x, and it has this property. You're right. If you can adjust x all the time to make it negative y, that's true. But we can't adjust x. The point is it's one specific number. That's the key.
There was an example earlier in this this meeting where it was where x did have a y value.
Yeah.
It was like y plus 1 or something.
Where were we? Here, right? And so this statement, we were trying to prove this statement, right? So here we're saying for all y values, based off that y value, there is some x value. But that's like one for each. In this case, it's like there's an x value for each of these. Right? For all y values, there's some x value that makes this true. It's a little ambiguous. I understand the confusion here. This is saying this is saying for all y values, for each of them, there is some x value that makes this. If the order was different, then it would mean something different. If the order was different, if it's saying there is an x such that for all y this is true, then that would be. So the order here matters. Hopefully that makes sense.
Yeah, I see. Thanks.
Yeah, no problem. yeah, 1y to 1x in this case. For every y, there is some x value that we can find. And this, I'm saying, this is the algorithm basically to figure out how to find that x. There's lots of algorithms to solve that. Right. Okay. Hopefully that made sense. Let's try the next one. And yeah, go ahead. Question. Go ahead, but you know, by all means. We can't use floor and ceiling functions. You can just disprove. You can just negate and prove via counterexample. Absolutely. Okay. So let's see. Next question. I'll do a couple more from this. Like I won't do all of them because I do want to move on. Someone has a hand up. You can go ahead and talk if you'd like, but not hearing me, or maybe hearing me, but not able to unmute. So for all y, this one's saying for all y, there exists an x such that x is less than or equal to y. This is true, right? So it's saying for each y value, there is an x value. Yeah, this is like, yeah, it is something to get used to for sure. But yeah, the way you think about this is like for each x value, for each y value, I mean, there is some x value such that this is true. This is definitely true. You can just choose x equals y. So what you want to do is you want to generate some way to find this x, right? So for y equals 5, there exists some other number such that this is true. X, this other number is less than or equal to 5. You just choose that number to be 5. So you can pick this. You can pick this. Pick this. Or really what we're doing is we're finding an algorithm. Find alg to generate x. That's like kind of more what we're doing here. Pretty much, if the existential quantifier is used first, there has to be a one value that is true for all the values. But if the universal quantifier is first, then there can be a different value for each value. That's correct. What you said is correct. Question. Hand up. Go ahead.
Sorry, I was the one that raised my hand last time. And
Don't
I was
worry.
trying to get my microphone to work. Can you
No
go
problem.
back to question A that I'm assuming this person sent you? The same one?
This one?
Yes. So why do we need the floor? Because we say... Actually, never mind. I see it.
Y has to be an integer, right? Y has to be an integer.
Yeah.
That's
if we say... If we leave it as x is greater than 2y and say y is x over 2 minus 1 and then plug it in and it all cancels out, would that be fine?
But y, but that would be fine if this was an r here, but y has to be an integer. Y has to be an integer.
So
right?
y can never produce an integer along any step of the journey, even though it cancels out at the end.
Yeah, y can never be a real number along any step of the journey because it has y has to be an integer. It has to be an integer here. Basically, like if I have any number here, like if I have like 2.75 here, divide that by 2, then that's not an integer, right? I can't assign an integer to that. I can't find. So we're basically trying to generate a way to like figure out this integer y, and I have to always set that to equal to an integer. You are right though. If we're looking at real numbers and you substitute that in, then yeah, it'll work out. Okay, good. So that's that. Let's try another one. And I got a couple more here. This one's not too bad. Yeah, it's some good questions here. Okay. So, started recording again. Yeah, I did. So, 2a plus 3 minus 7 is odd for any integer a. This is true. And I'll just show you why. So a plus 3 is an integer. So I'm just going to immediately replace that with like k, something. So this is 2k minus 7. And I want to show odd, right? Odd means it's 2 times something plus 1. Or minus 1. Doesn't really matter. I like plus 1. So I'll rewrite this as 2k minus 8 plus 1. Why would I do that? I want this plus 1 at the end. And I need to keep this equal, right? So it's the same as this. Okay, but now I can factor out that 2. This is 2k minus 4 plus 1. K minus 4 is an integer. I'll just call that k2. And there we have it, 2k2 plus 1. So that quantity is really just an odd number. There we go. Good. That's great. Anybody has any questions, feel free to jump in, raise your hand. Or you don't have to raise your hand. You can just unmute if you want. But if you want to be nice and raise your hand, that's welcome as well. Or just type in the chat or whatever. Good. Okay, these are good questions. We have time, right? Yeah, we have. If n is even, then n equals 4k for some integer k, or n equals 4k plus 1 for some integer k. Yeah. So why did I add 1? I just needed to make this, I need a plus 1 because that's the form of an odd number, right? An odd number has a plus 1. Or I don't know if you guys do a minus 1 or a plus 1. It doesn't really matter. You can just put a minus 1 if you want, but basically it's like 2 times some integer plus 1, right? That's what an odd number is. 2 times. So if n is even, then either this or this. Yeah. So if n is even implies n equals 2k. If I just write k as 2k2, right? Or there's a lot of ways to do this. I'm trying to think of just like the clearest way. That's what I'm thinking of. I'm just trying to think of the clearest way of doing it. So this is clearly an even number, right? Because 4k is 2 times 2k. 2k is just some number, right? So yeah, if n is even, which means it can be written as 2 times an integer, then it can be written as 2 times an integer, or whatever else. Doesn't matter. It doesn't really matter. Basically, this is saying if n is even, this implies n is even, or whatever. Definitely true though, right? Definitely true, regardless of anything, right? Because n equals 4k. Actually, sure, it implies that it's a multiple. N is a multiple of 4, but that's also even number. 6 can't be expressed in either way. 6, sure, but k is 6 can't be expressed in either way. You're right. 6 can't be expressed like this. 6 can't be expressed like that. That's true. That's a good point. Why can't it be? Couldn't you just do 2 times? You could do multiple 4, or it's 1 off of multiple 4. Since k is bounded by an integer, yeah. N equals 4k really seems like, so that's going to be even. I'm just stuck on the fact that this definitely means even, but I guess it's more than just even. Okay. Yeah, I see that. So, okay. Yeah, I'm willing to accept that then. Thought that would be n is even. And n equals 4k for some k. Why does this not work? 2 times 2k. 2k is an integer. Yeah, but I guess but then k would have to be, that means it's an even integer. 2 times an even integer. And 6 is not 2 times an even integer. Okay, yeah, that makes sense. So it's more precise than what I was saying here. Yeah, so okay, just by counterexample, basically. So if n is even, then basically let me be more precise with what we're saying here. If n is even, this implies n is a multiple of 4. Multiple of 4, or n is 1 above a multiple of 4. Yeah. So that's what we're saying. So this is not true. It's more precise than I was thinking, right? You can just do by counterexample, right? So 6 is not a multiple of 4. It's also not one off of a multiple of 4. So there we go. That's it. So counterexample. Okay. Hopefully that makes sense. Any questions? Feel free to let me know. Let's get the last one done here. Oh no, we did this already. If xy is odd. Oh. Well. If xy is odd, then both x and y are odd. So xy odd implies x odd and y odd. I'll just flip this, right? So x even or y even implies xy even, right? So reverse the order and negate everything, right? True by contrapositive, exactly. So if either one is even, then the result's going to be even. That's the claim we're making. So let's see. I just try it. So if x is even, so yeah, if either one are even, so it's either one, both, or the other one, right? So x, it doesn't really matter. I just have to check if one's even, if one is even, and I have to check if both are even. If both are even. So that means let's just choose x to be the first one. X is 2k. Y is, let's say not. Let's say 2k plus 1 or 2k2 plus 1. Then xy is 2k1. Xy is 2k1, 2k2 plus 1, which is 4k1, k2 plus 2k1. And this is even because it's 2 times 2k1, k2 plus k1. And so that's even. So that showed this, and I just have to check the other case here now too, right? I have to check if x is 2k1 and y is 2k2, so both even, then xy is equal to 2k1, 2k2, which is 2 times 2k1, k2, which is even by definition. And so also true. So yes, true by just contrapositive. Okay, and then I got one last question in my email, which we'll talk about now for the last 2 minutes. And then we will finish up. Nope, did not save for some reason. There you go. So can you please solve questions 39 and 41? Good. Absolutely. In if-then form. So earning a grade of C- in this course is a sufficient condition for it to count towards graduation. Okay, so sufficient conditions and necessary conditions. We got to just remember what this looks like. So I'll just go back to this sheet here, and then then we have this to remember. Oops, that's not what I meant to do. To open it. So R is what are we looking at? We're looking at a sufficient condition. So what's the sufficient condition for what? So earning a grade of C- in this course is a sufficient condition for it to count towards graduation. So R is sufficient for S means R implies S. So that means that if I get a C- in this course, if you earn as a U, if you earn a C- in this course, then it counts towards graduation. right? So it just kind of matching. And sufficiency means that like what you're doing is enough for the conclusion, right? Whatever happens, that's enough for the conclusion. Necessity is kind of opposite way around. If something happened, then by necessity, something else happened. So being on time each day is necessary to keep the job. So if R is necessary to keep the job, that means if you're keeping the job, you must be on time each day. So you see how like the conclusion, not the conclusion, but the event implies that something had to happen. So if you're keeping the job, you had to be on time each day. So that's what it is. Well, I guess you can write it like this. But if you, being on time is a necessary condition to keep the job. I guess this is a little bit more precisely what's going on. Is if not R, then not S. Right? So that means like if you, it's kind of the same thing. But it doesn't really matter how you say it. This is the way to say it. That's not how I would write it, to be honest. But anyways, let's just match this because this is what you're gonna have on the formula sheet. So R is a necessary condition for S. Being on time is necessary to keep the job. So if you're not on time, each day, then you lose your job. But if you keep your job, another equivalent way of exactly saying this, which is probably how I would say it, if you keep your job, then you must be on time each day. Then you must be on time each day. Right? 43. A prime number is prime if it is greater than 1. So if a number is prime, then it is greater than 1. Greater. It says only if. Oh, only if a number is prime. The other way, so if it's greater than 1. It says only if. So a number is prime. No, this is right, I think. If it is a number is prime only if it is greater than 1, which means this is right. I think this is what I wrote is correct, because again, I know I'm just kind of repeating it over and over again, but a number is prime only if it is greater than 1. So the only time a prime number can be prime, anytime a number can be prime, is if it is greater than 1. So if a number is prime, that means it must be greater than 1. Right? So you can say being prime is sufficient for 1, or be greater than 1, or being greater than 1 is necessary to be a prime number. It depends on how you want to phrase it, right? Okay, so no, it's not only sufficient or necessary. Yeah, depends on how you want to phrase it. It's sufficient and necessary, I guess. In this case, sufficient and necessary. Yeah, so I guess in some situations it is only one of the two, and that depends on the phrasing. But here, no, it's not sufficient. It's sufficient this direction. Conditionals and biconditionals, yeah. So like, this is a great example, right? So prime implies greater than 1, right? But the other way is not implied. Greater than 1 implies prime. That's not true, right? But biconditionals means both ways. So even implies 2k. Other way around is also true. Hopefully you know what I mean, right? Like the number can be written as 2k. Even, these are biconditionals. These are both ways. But prime is greater than 1. That's true. A prime number is always greater than 1. But a number greater than 1 is not always prime. That's the difference there. Okay. Question. Go for it.
For the sufficient and necessary, like, would you always be given that keyword, or like if it's not given, how would you know?
yeah, so maybe let's look at this here, right? So passing a comprehensive exam, well, that's necessary. That's necessary. Never mind. So yeah, I mean, you just want to sort of basically a good way to do it is like think about this. Think about like are both directions implied here? Because that'll help you decide what's important, right? What do we actually know as a fact? So what we know as a fact, for example, here is that if a number is prime, then it has to be greater than 1. Right? I didn't actually have to even decide if this is sufficient or necessary. But yeah, what would it be in this case? I mean, we would say that a number being prime is sufficient to say that it's greater than 1. Right? But, and the other way around too, I guess. A number... I have to draw it, so I can't just say it in my head. A number... Come on. Doing a weird thing. Let me just fix it. There we go. Let me move this here. So prime is sufficient. No, greater than 1 is necessary for being prime. Okay. That's correct. So being greater than 1 is necessary to be prime. Prime is sufficient for being greater than 1. These two statements are true. So being greater than 1 is a necessary condition for being prime, and being prime is sufficient for being greater than 1. But so these two are true. These two are true. The next two I'm going to write are false. So greater than 1 is sufficient for being prime. This is false, right? There's lots of numbers greater than 1 that aren't prime. So we're saying that knowing this is enough to know this for a fact, but that's not true. Knowing this is enough to know that this is a fact, but knowing this is not enough to know that this is a fact. 3 is a prime number. 8 is greater than 1, but it's not prime. And then the other way around too, right? So if I have prime is necessary for being greater than 1, that's also not true, right? It's not necessary to be prime if the number is greater than 1. These are false. So maybe writing out all the options like this is a good way to do it. If necessary and sufficient aren't explicitly written in the question, we have to infer it based on the statement and the way it's expressed. That's my understanding. Okay, guys, we're wrapping up. It's 8:08. So that's our time for today. I'll stop my recording here.